So next talk is given by the Wenzel Jakob. And the title of the talk is Capturing, Simulating, and Differentiating Light. Okay.
Okay, I think we can turn on the lights a little bit. Always a pleasure to be in Japan, so thank you very much for inviting me to the Shitsukan project and Dobashi-sensei. Just a few words about myself. I'm an assistant prof at EPFL, and my research is about capturing the way that light interacts with the world around us and then building efficient algorithms to reproduce that in computer simulations. And so apart from the research, we also build a lot of software in my group. Some of you may know this book. It's the foundation of PBRT. And then there's a Mitsuba renderer and also various other open source projects. And some of those are used in, some of the algorithms are used in commercial products and in the movies. And I'll talk about two things today that are things that we've been recently working on. And one is a new generation of rendering framework that we call Mitsuba 2. And then in the second part, I'll talk about material measurement, because I think that's potentially also interesting to this audience. So first, to set the stage a little bit, what are the kinds of things that we're interested in when we do rendering? So this is actually a photograph, I should point out. So we have direct light that's arriving from the sun that, for instance, you can see here how it takes some of the red color to other objects. There are specular interreflections. There's the absence of light due to scattering. And then refractive objects focus light into these interesting patterns called caustics. Light that goes into a material like milk can interact hundreds of times with all the little fat bubbles inside milk that gives it its glow. So if you don't simulate that, the milk will be disgusting. So it's going to look like paint. And so all of these are things that we want to simulate when we make computer renderings, because they cause the images in the end to look realistic. Another way to think about this is that all of the objects that you see here are talking to each other through light because of this interreflection. So that means that if I change any part of this image, it could potentially affect any other part of it as well. It also means that just by looking at an image, it can be difficult to reason about what the properties of something are. So for instance, if I did a sort of a crop of this laptop here in the back, I think it might be difficult to know what color it is, because the color is actually influenced by the objects around it. And so basically, bottom line is to understand what's in such an image, we need to understand the world around it as well. And that's sort of, it's interesting from a realism point of view, but it's also interested in trying to understand these kinds of images. So far, my own background is that I've approached the generation of these kinds of images with the goal of making them as realistic as possible. And so I'd mentioned that I've been developing this rendering software that's called Mitsuba. This is fairly widely used now in the research community. So every year there are some papers at SIGGRAPH Asia, and so on that build upon it. It's a modular code base with about 120 plugins. Plugin can be a light source, it can be a material, it can be a rendering algorithm. And I think that's one of the reasons actually why it's popular, because usually when you're writing a research paper, it's like one plugin, so you don't have to worry about all the other stuff. You can just focus on your own little corner. And it's pretty big, about 180,000 lines of C++ code. And this is something that I started working on during my PhD, but that was a long time ago, and it's lacking some things that have become interesting to the world since then. And so the first thing is spectral rendering and polarization. These are things that are actually not that difficult to simulate, and so if we want to really capture physics, we should account for those as well. Another thing that's maybe a little bit more kind of engineering related is vectorization. So Mitsuba, the original renderer, was propagating one light path through a scene, and then it did the next one, and the next one after that. And nowadays we have GPUs and we have vectorized processors, and these can do many things at the same time. And if you don't actually make use of that, it's not going to be very efficient. And then the last thing, and this is really a super new topic. So like in rendering, this is like the first paper that did it properly was 1 year ago. So it's really a brand new subfield of graphics, if you want to call it that way. This is also something that's become quite interesting. I'm going to talk at length about what that is because I think it's very interesting, and many of you probably haven't heard of that yet because it's so new. In any case, because these things are quite interesting, and there wasn't really any way of putting them into this old system, we've decided to build a new renderer, Mitsuba 2, from scratch, that is able to do some of these things. And so I'll just dive first into this one sub-feature, differentiable rendering, and kind of ask, what is this actually good for? So normally in a rendering algorithm, we're starting with a number of parameters, and that could be the geometry, so basically the triangles that make up the scene, the materials, textures, light sources, and so on. Basically, think of like a big set of floating point numbers that specify the scene. Those are the input parameters. And that could be like 10 million numbers. That's not an unreasonable amount. It could be 100 million. Anyway, it's lots and lots of these numbers. And then we do a simulation, and that gives us out a realistic image at the end. And this simulation, you can really think of it as a kind of a function of these input parameters. Now, this function, it encodes the physical process of light scattering. And one interesting question that you can ask yourself is, can I compute a derivative of this function? So, in that case, I want to know, like, how does the output image change if I wiggle around some of the input parameters? And so, that's a reasonable thing to ask. But then we also need to use it to do something. So we need to specify a goal. What do we actually want to use these derivatives for? And so for this, we will add a loss, some kind of an error metric. So for instance, you could say, oh, well, I don't actually like the picture of this bathroom. Maybe I want it to look more like that. So let's take the difference between these two images and add up all of the pixel errors. Then I get one number out in the end. And then you could say, well, what are the derivatives of this error with respect to all of these input parameters? So this one number, it's called the loss. And then you can do an update to the parameters of this scene. Basically, what this tells you is that in this 10-dimensional space of parameters, what is the direction in which you should walk to get closer to where you want to be? It's a very similar algorithm for optimizing neural networks. If you're familiar with that, it's called backpropagation. Basically, that's what we're doing here. We're doing backpropagation through a rendering algorithm. Now, if you're going to do it like this, I'll just say that's probably not going to work very well. So you have to be a little bit more careful about setting up your optimization problem. But we'll get to that. So what do these derivatives look like? Well, here you can see some examples. This is a Rubik's Cube, and on the right side is now the derivative of this image. And I think it's a little bit hard to see, but there, I think it's hard to see. Well, you should be able to see actually a reflection. And so what I've done here is I've computed the derivative of this image with respect to the color of the front faces. That's one of these numbers. And because light is interreflecting and everything is kind of talking to each other through light, you get also some derivatives there. Or you could say, what happens if I move around the top here a little bit? You get some derivatives. What if I move the whole cube to the side? Then you also have something in the shadows. I think it's very, very difficult to see. Well, a little bit too contrasty, this beamer. Or I can say, like, OK, let's move the light source. Then I get some really strong derivatives in the background. Anyway, so this is sort of one way of using derivatives. You can say, what if I wiggle around one of the inputs? How does it cause the output to change? But the really interesting way to use it actually is the other way around. So you could say, what if I wiggle around the output image? What if I want it to look more like something else? How do I have to change now all of these 10 million input parameters? And this is something that you can actually do with differentiable rendering. And you can use that for a number of applications. And before telling you how it works, I'll just show you some of these applications. And so the first one is 3D reconstruction. Imagine that you're given a bunch of images of an object that you want to reconstruct. So these are really just images. And then we start with some sort of generic shape that's at least roughly similar to where you want to go. Then you can run a differentiable rendering algorithm and ask it to get closer and closer to that. And so you can see how the shape is sort of starting to deform. And then it even pushes out the little bumps of the starfish. this is actually pretty easy because this image on the right is rendered, but you can also start with a photograph. So for instance, this is an actual pair and a few photos from different sites, and then we can start with the screen blob and then just run a rendering algorithm and say, okay, how do I get closer and closer and closer to this pair? And then you end up here in the middle. So this is a kind of a wacky way of doing 3D reconstruction that's quite different from what is currently used in computer vision. It also works if you just have a single image. So for instance, here we took this image from the moon of this famous bootprint, and we said, well, the moon is kind of diffuse. Light is coming from one direction, only from the sun. So can we actually reconstruct now the height differences as a consequence of this moon boot? And then we can render it from a different viewpoint. It's really important to account for these indirect effects, basically light talking to each other, and in particular the shadows. So for instance, in these images, shadows are actually a big clue. So if you don't account for them, the reconstruction you get is not as good. Here you can see it also with the pair, that you get a really jaggy shadow. The shadow is actually a hint of how high the surface should be in a different place. So all of these are examples where I'm showing direct reconstruction of an object. But remember that light is interreflecting, and so an object also has indirect effects on its environment. And this is also something you can optimize with a differentiable renderer. And here's an example of that. So imagine you're in a museum, and there's a light source, and then there's a glass panel here in the middle. It's really dark. And so anyway, so we're saying, okay, can we change the height of this glass surface so that the light actually gets focused into this famous image of the great wave? And then we can compute a modified glass panel. And it's, again, a little bit hard to see. But this is now rough. So one side is not perfectly smooth, but it's sort of undulating, going up and down a little bit. And then we can get closer to, we can reconstruct this image. Or we can also start with colors. What if we have a colored light source, and then we want to optimize a certain target image? Then we actually need to modify the object so that it mixes these colors in just the right proportions so that we can get closer to this target. Now the object is moving around, so then of course the caustic is also changing. Here is an example where we have a cube that's made out of a solid block of glass. And now what we will do is we will change the index of refraction at different places inside this cube. And then as a consequence, what's actually happening is that light is moving along curves. And we can use that to put two different images into this glass cube. So we got Einstein on the left side and Turing on the other side. There isn't really any 3D printer that you could use to make something like that, but maybe one day there will, and then here's an algorithm to make content for it. Yet another example is volume reconstruction. So if you have a cloud of smoke, then using a differentiable rendering algorithm, you can reconstruct the density on the inside, including things like multiple scattering of light. And if you do it like this, naively, it's probably not going to work very well because that smoke looks perfect from one side, but the moment that you rotate it around, it does something completely different. And that's just because we didn't have enough information. We need to constrain it more. And so what you would actually do in practice is to use a few different views and then optimize with all of them at the same time. So the last example, and that's my favorite one. So here, imagine that you have a 3D printer that can print colored 3D objects. There are fancy printers like that now that can put little color droplets inside a translucent material. And when these printers became available, what people immediately did is that they downloaded colored 3D meshes from the internet, and they printed them on these printers, and they look terrible afterwards. And the reason for that is that they're very translucent, so that means light goes inside, and it kind of bounces around and comes out somewhere completely different, and that blurs together all of these colors, so you lose all of the contrast. The question then is, can we actually compute what ink droplets we should put down so that taking into account this interreflection, it looks closer to what we wanted it to look like? And so here we start with a target. Suppose this is what we want it to look like. And then once we turn on the subsurface scattering, we lose a lot of the contrast. You can see, for instance, that the clouds are really blurred out. But after running a differentiable rendering algorithm and sort of asking, how do we get closer to the reference, we can reconstruct some of those details. So those are just a few examples. So what's actually interesting is that for many of these examples that I've shown before, there were papers about how to do this, SIGGRAPH papers or in other conferences. The nice thing about this here is that that's really just a few lines of Python code. You run your differentiable renderer, you're not happy with the result, and you compute some kind of an error, and then you do a gradient step. So it's pretty easy to do all sorts of optimization with this. So how does it work? So our system is split into two parts. One is Mitsuba, the renderer, and another one is a library called Enoki. So the top part is responsible for light transport, and the bottom part is responsible for the computation, the actual arithmetic. The whole rendering system is implemented in a way that is generic. So it sort of depends on what is the floating point representation and what is used to represent color spectra. And then that allows us to create many different flavors of rendering systems depending on what we want to do. Maybe we're interested in differentiable rendering, maybe we're interested in polarization, maybe we're interested in spectra. So there's like a whole family of different rendering systems that you might be interested in and that we can create on demand. And then we can sort of open up the boxes, and then there's a lot more complexity. And I'm not going to talk too much about that. I'll just give you a bit of a flavor of two particular parts. One is the CUDA backend, and one is the autodiff backend. And this is actually what we use to implement this differentiable rendering. So for the CUDA backend, what happens is that, well, our renderer is written in C++, and it uses floating point types to do all of the calculation. And here now we use a special type that is provided by this Enoki library, and that's called a CUDA array. It means that it involves computation that is stored on the GPU. And then once we execute some math with this type, what actually happens in the background is that our system creates a kernel using a programming language called PTX. This is something that can be uploaded or can be compiled for NVIDIA GPUs, and then it runs really efficiently on this fast hardware for doing parallel computations. These kernels are furthermore cached. So for instance, when we run optimization, usually we don't just make an image once, but we make it hundreds of times until we get closer and closer to where we want to be, and then we can reuse those. And the second part is the autodiff backend. Again, here, when we do some calculation now, our system does some extra stuff, and in particular, it keeps track of the computation graph that is created by this computation. And this is necessary to propagate derivatives, because the algorithm is called reverse mode automatic differentiation. And so what that actually entails is that we take this graph and we propagate it in reverse, and we propagate the derivatives to the input parameters. And this is the key insight that lets us compute derivatives with respect to, let's say, 10 million parameters at the same time without having to run the rendering algorithm 10 million times, which would be very, very slow. So one interesting thing here is, you might have seen that these types, they are actually nested into each other. So we have like CUDA array of diff array. I guess this will only make sense to the C++ people in the room. But what that actually means is that this graph is then also compiled into this PTX language that I had mentioned before. And so that basically is the kind of the key technology that allows us to do efficient derivative computation of very complex simulation code on the GPU. And these computation graphs, they tend to be very, very big. And so this is not even like a fraction of a %. So when we actually generate visualizations of these graphs, you get like a 100 megabyte PDF file. It's completely pointless to even look at it and try and understand what's in there. So, but we have software to help us with that. So I think it's actually a really exciting time, because differentiable rendering is a bit of a game changer in what it allows us to do. So far, my field, rendering, has been very focused on providing technology for the visual effects industry, the movies, basically. When we were working on a project, and then, let's say, that was used to make some character in a Marvel movie look a little bit more realistic, that's sort of the ideal outcome for a project. But I think with this ability now to tackle fairly complex inverse problems, it's really an opportunity to connect to many other fields that are working with images and help them solve some of their problems. So I'll just give you a few ideas. Architecture, for instance, is one. There's a field called daylighting that seeks to optimize architecture so that it makes efficient use of naturally available sunlight. If you're in a building, it's usually really, really bright close to the windows, but then when you go deeper inside the building, it's too dark and you need extra electric lighting. And so the question in daylighting is always, how do we change the building so that we can get more use out of this sunlight? And so there are a lot of kind of tools that they use, but it's mostly based on intuition. So with our approach, we can actually differentiate the building with respect to what the architects want to do. So they can specify, I want it to be a certain level of brightness inside the building, and then we can say, well, which parts of the building are now sensitive with respect to achieving that goal? How would the building want to deform to be able to do that? These kinds of things. So it's pretty exciting, and we're starting to work with some architects on that. Medical imaging is another interesting application. So in CT scanners, that's based on the radon transform for reconstruction, and this is looking at how much light is absorbed along rays going through the volume. But X-rays are not only absorbed, but they're also scattered, and this is actually something that you can simulate with a differentiable renderer and then potentially do a better job at reconstructing media. Yet another example, astronomy. So when we look at images in telescopes, what we see looks a little bit like a volume rendering, and that's actually not a surprise because the volume rendering equation that's used in graphics was imported from astronomy. And so that means we can actually do a differentiable rendering of, let's say, an interstellar cloud or a galaxy based on a model that somebody has come up with, and then we can compare it to what we're seeing in the actual telescope to try and improve the model. So these are just a few samples. I think there are many, many more directions that have to gain from differentiable rendering. So that's a very quick tour of differentiable rendering. Now I'll talk about one more thing. And so in my lab, we are also doing empirical measurements of materials. And so there, what we want to understand is when light arrives at an object, where does it go afterwards? Because that's ultimately what makes it look the way that it does. And this is captured using a function called the BRDF that was already mentioned several times in the morning session. So it's a function of two directions. Where does light come from, and where does it go afterwards? Actually, it depends also on the wavelength. And so here's just an example where we have light incident from different directions. Then this is the direction where it goes afterwards. And so if we can characterize that, then we know a lot about this material. And so how do we measure something like that? Usually, you need some kind of a machine that can observe a sample of some material from different directions, and you also need to be able to move around the light source. So this is two dimensions, this is 2 dimensions, and this is 1 dimension. So it's a 5-dimensional function, and this is usually bad news, because then that means we're deep in the domain of the curse of dimensionality, and it's just kind of very painful to measure these kinds of things. But let me first show you what the machine looks like that's used for this. This is a gonio-photometer, which is built by a German company called PAP, and it has a light source that is static, so it doesn't move around. It's usually pretty heavy, so we'd rather have it in the same place. There's a sample holder that can move around, and then a detector that can also move around. This is what it looks like when it's installed. So that's the light source part, and then that's the sample holder. This is pretty big, so you can mount something that's about a square meter almost. And the whole machine is about 5 meters from one end to the other. So it's really the kind of thing where you build a room around the machine rather than the other way around. It's in a room that has black fabric on the walls so that light which is reflected from the sample is absorbed. And then on the sensor head, there are kind of different modules. We can only measure the reflectance or also the reflectance spectrum. We can mount cameras if we're interested in spatial variation. And when this machine runs, this is kind of what it looks like by default. The head moves with about 3 meters per second, so it's seriously lethal. If this hits you on your head, it's not going to end very well, and that's the reason why it's in a cage. So you really need to lock the door before you can even turn it on. And so this looks pretty nice, right? If the machine is moving this fast, it should be pretty fast also to finish a measurement. But unfortunately, this is not true. Let me just give you an idea of why measuring BRDFs is hard. First of all, let's suppose that we're discretizing the domain now, let's say with 100 by 100 points, and now we have our machine move through all of these, and let's suppose we do 1 measurement per second, just for ease of calculation. That means actually that it will take 3 years of measurement time to finish even one material. So that's the curse of dimensionality for you there. So the machine would probably break down before we even got a single material in the box. So what do we do differently? Our high-level idea is that where we want to measure the material is actually different depending on what it is that we want to measure. So for instance, for a piece of paper, that's kind of very diffuse. We want to measure more broadly. Whereas if we measure something that's kind of like a mirror, then we probably only want to measure close to the mirror reflection. And the second observation is that in rendering algorithms, there's one operation that we have to provide, and that's really essential to do simulation, and that's called importance sampling. And so in importance sampling, we pick points proportional to the magnitude of a function. And so that's actually kind of interesting because this brings us to places where the function is non-zero. So that suggests an algorithm for measuring, which is that we importance sample a point, and then we drive the machine there, and we measure it. And that should seem like a pretty nice algorithm. Unfortunately, there's a chicken and an egg problem here, which is that to be able to importance sample the function, we actually need to know what it is. But we're trying to measure it. We don't know it yet. So how do we get out of this chicken and an egg problem? So our insight was that maybe there's something else, and in particular something that's faster to measure, and that's informative. So by informative, I mean that we can use it to build such an importance sampling scheme. And it turns out that there is such a thing, and it is the retroreflection. And so here the idea is that we take this BRDF, and we simply plug in the same direction twice, and we also fix the wavelength. So here we just use a green laser. And then if we look at this retroreflection, we can see that it's rather different. So for instance, a diffuse material, it's quite spread out. For a metallic material, it's much more concentrated. For a brushed metal, that is anisotropic, so it means it reflects more light. Well, so the reflectance depends actually on how it is oriented. So we can actually distinguish between these three. So I'm not going to go into more details. I'll just give a basic motivation. So in essence, once you know this retroreflection, you can build an importance sampling technique for this material based on what is known as microfacet theory that was already mentioned earlier. So basically, like if this was a microfacet material, and you know the retroreflection, then you know everything there is to know about the material. So then you can also importance sample it. And that turns out to be enough to find sort of what are the interesting places in the space of this material. I can chat in more detail later if you're interested in that. Measuring retroreflection is actually a little bit tricky because what it actually means is that this arm here would be in the way. You know, if we move it to the place where light is coming from, then we're actually blocking the light. And so the way that we do it is that we actually have two different beam paths, one for white light and then one for laser light, this green light. And here is something that's called a beam splitter. And that's sort of the trick that we use to allow us to measure retroreflection. And then this is what it looks like. So our machine begins first measuring the retroreflection. And this is really fast, I should say, because it's only two-dimensional. Here it's even one-dimensional because the material has a rotational symmetry. So this takes no time at all to measure. It's much, much faster than measuring the whole material with brute force. And then once we're done with that, we know what are the interesting directions to look at. And so you can see that the machine behaves very differently now. Instead of spinning around like crazy, it's driving in a much cleverer way to the relevant places and doing point measurements there. So that's kind of the technical foundation of our current project, and we're using it to assemble a large database of materials. Right now, I think there are about 70 or so. Our goal is that eventually we have many, many hundreds of materials. We want to really sample the whole space of things that exist. once we've measured materials, we can, of course, put them on different objects. These are some pearlescent and color-changing paints. Here is a kind of a pearlescent material, for instance. We're measuring insects as well. So here's a morpho butterfly. If you could have a sphere that was made out of morpho butterfly, this is what it would look like, or a dragon. We're also measuring fabrics. So this you may have seen. Sometimes you have a silk that has sort of one color from one side and another color from another side. That's a typical kind of anisotropic material. And all of this is available for free on our website. I will just show you this page. 1 second. Basically, you can even send us stuff and we will measure it for you for free. I know it's an amazing deal. And so the catch, though, is that it will be in this database and everybody can download it under a CC0 license. So you have to be OK with that. Surprisingly, even some movie companies were happy with that. So we've measured the pants of Darth Vader and some pieces of the Millennium Falcon. I would have thought the lawyers will say no to that, but they were OK with it. So anyway, so in this database, you can basically browse some of the things that we've measured so far. You can click on them. You see basically like what is the representation of the material in our database. You can see the material with different illumination environments. And then this button is a lot of fun. You can press an interactive viewer, and then it starts a program that runs in WebAssembly and WebGL in your browser. So here you see now basically where light went after it was received by the object. It's a hemisphere which is projected down to a disk. And the higher the function is, the more light was sent into a certain direction. So now, first of all, light is coming from the top. And I can select this point, for instance. And now here on the side, we see the reflectance spectrum. So it goes from UV to infrared. And because it's a kind of a pearlescent material, there are some interesting wave optical effects happening here. That's why the spectrum is oscillatory. I can now move also the light to a more grazing configuration. So now light is coming from close to 90 degrees. And you can see that the color changes. So it goes from sort of greenish to bluish. And then eventually it gets really spiky. So this is a grazing angle reflection now. And we can also take a look at the spectrum. And we see that it's becoming brighter towards infrared regions, which is an effect that's still an ongoing research topic. It's called the reddening effect. So that's a sort of a fairly standard material. Let's look at this morpho butterfly. That's much crazier. All right, it might take a few seconds to load. So I guess this is a very strange material that's very different from any current models that are available in computer graphics. These kinds of things I think are exciting because they enable the development of new reflectance models. So here, yeah, I would say that probably nobody really understands what is happening here. All right, and that's actually all I was going to talk about. So if there are any questions, I'd be happy to take them.
Thank you. Any questions, comments?
All of the stuff are very exciting, but yeah, okay. Just one question for your daylighting simulation. That's really exciting. But I just wonder that if you already have a building,
yes,
can you do the same thing, right? So you don't know the rendering model of that situation.
Not sure I understand the question.
So for example, you already own a building.
You already own a building. Well, then it's difficult to change. Well, I guess some of these daylighting components are rather modular. So something that people sometimes do is they have these prismatic sheets they put on windows, and then when the sun is coming like around noontime, it's almost coming down vertically. These prismatic sheets sort of refract the light back up so that they hit the ceiling inside the room, which then gets turned into a light source, and that pushes light further into the building. So like even if you have already
but you need to have a 3D models or a lighting models of that.
Aha, that's the sun actually, right? So we know exactly the way that the sun moves and you know, throughout the day, throughout the seasons. So you will probably want to simulate a whole year actually. So that's a pretty long rendering because the sun is constantly in different places.
You need a perfect model of the building and the materials and.
Yeah, I mean, but I mean that's what you have as an architect. You know where the walls are. You probably have a good idea of what type of paint will be used. I think it's a little bit effort in putting that kind of system together, but then that can be used to give you a sort of a reasonable guess of the performance of the building. I think the more difficult thing in architecture is it's not just the sort of the daylighting constraints, but there are also aesthetic considerations. So you want things to look symmetric and well balanced and so on. So these kinds of constraints can of course fight with what the simulation is telling you to do.
Thank you.
So I think I already kind of asked you the question at lunch, but again. Do you think it would be possible to actually try to match these kind of materials, starting from a complex description of a layered material, and using differentiable rendering to recover the physical parameters of the layered material?
Yeah.
Yeah.
I think well, you know. It's an optimization problem, and optimization problems can potentially be very nonlinear. So what does a differentiable renderer tell you? It gives you derivatives, which is a very local thing. So it's telling you sort of, you know, at the place where you are, if you take an infinitesimal step into this direction, then you'll get better at, you know, at your problem statement. So
you mentioned
derivatives can help a lot during the optimization, but it's not always the only, sometimes it's not enough to just do that. So for instance, actually, in some of the example applications that I've shown earlier, what we actually did is we had kind of multi-resolution descriptions of the scene. So for instance, with this glass panel that was creating caustics, we actually started by doing only some very kind of low frequency height variations to just sort of get the light into the right place. And then we optimize that for a while. Mm-hmm. Then we increase the resolution a little bit. Then we optimize again for a while, and so on. So, you know, these kinds of things, they are just as important as having access to the derivatives, so that you can find a way in this very non-convex optimization landscape to find a way to the solution you want.
You also mentioned during lunch that it starts to make sense when you start to have lots of parameters.
Yeah.
So
yeah.
Can you comment a little bit on that?
So this differentiable rendering, it's pretty hard, I would say. Actually, I forgot to, now that I think of it, there was a slide I wanted to show, and somehow it was not shown. So let me just bring that up. Basically, this differentiable rendering, it's pretty hard. Where is it? Come on. Yeah, here. So what are the problems? First of all, this computation graph that you get, it's really a mess. It's huge. I mean, huge doesn't begin to describe it. So you cannot do this differentiable renderings, for instance, with the standard frameworks that people use for differentiation, like PyTorch, TensorFlow, and so on. It just doesn't work. And the reason for this is that light spreads out. It sort of goes all over the place, interacts with different materials, and that's what causes this computation graph to be so big. There is the whole issue of discontinuities. If you have an object in a scene, for instance, this table, this desk, it has a boundary. There's actually a discontinuity which is non-differentiable. How do you deal with that? If you just differentiate your rendering algorithm, you actually get the wrong answer. So there's quite a bit of complexity in dealing with that. Local minima I had mentioned. And then there's also the question of efficiency. Differentiable rendering is much, much slower than normal rendering. And so all of this just adds quite a bit of complex machinery. And I think it's really worth it when you're optimizing 10 million parameters at once, because that's really, really hard to do. And with differentiable rendering, you get the gradients of all 10 million parameters at the same time, while only having a rendering that's maybe 10, 20 times as slow. So that's pretty good. But when you only have 5 parameters you want to optimize, it's really overkill. So you can just do finite differences or something like that.
Thanks.
I have a question about differentiable rendering, or you call it like backward rendering, is it? Is that
there's an, the algorithm that's used to do the actual differentiation is called reverse mode automatic differentiation, and in the computer vision community, it's called backpropagation.
Okay.
Yeah.
So you guys use like a target, and it looks like a 2-dimensional image.
Could be anything. Could be a light field as well. Or, yeah.
Okay. So let's say it's like an image. So that means it's a 2-dimensional data, but can we get a rendered, like reverse rendering of that data to be 3-dimensional data, to be 3-dimensional image, something like that?
Of course, yeah. So because what the renderer has as input is a 3-dimensional specification of the scene, when you run a differentiable rendering, you're optimizing the scene parameters, which is a 3-dimensional thing. So, I mean, in some of the examples I showed, I was then changing the viewpoint and showing the thing that was created from another side. So because it is 3-dimensional, what gets created in the end, yes, that is something that you can do.
Is it the one with the smoke?
With the smoke, or with this moon, with the boot print on the moon, or for instance, you saw this this pear that was optimized, or the starfish. It's really a 3D mesh that comes out. And so when the problem is easy enough, you can actually optimize that only with a single view, like in the case of the moon boot. When you have a more complex object, you need a few different 2D images from different sides to start the optimization. But then what comes out in the end is a textured 3D mesh that you can view from any side.
Okay, one last question. For the target data, can it be like we have all the depth data as well? Like,
that can help a lot.
That is okay, right?
Yeah, yeah.
All right, thank you so much.
Yeah, any kind of constraint, extra constraint that you might want to add, as long as you can differentiate it, you can incorporate it in this kind of simulation.
And then in the end, you can get the rendered 3-dimensional image close to the real image, right?
That's the goal, yeah.
Okay, thank you so much.
Okay, so probably you may have more questions, but we'll take the coffee break, so you can, no coffee, only the rest, but you can continue to the discussion. So thank you very much.